hypothesis testing was really about parameter estimation, but trying to make decisions about that in a slightly different way than we do with confidence intervals. And particularly trying, when we get into comparative studies, this is an important tool that we have available to us. Right? So these hypothesis tests, and first we looked at single samples, are based upon sampling distributions of whatever statistic that we're looking at, the test statistic, if the hypothesis is true. And then we start to look at how likely it is that what we've actually observed would happen if our hypothesis was true. And so we had this notion here that you have, say for tests on the mean, we have a null hypothesis that said that, okay, our true mean was equal to some particular kind of value, call it mu naught. Right? And we had this possibility here that our null hypothesis was true, or the null hypothesis was false. Right? And the outcome here was that we could fail to reject our null hypothesis. We'd like to say that rather than we accepted H naught. Right? And in which case we would have no error if the null hypothesis was true. Right? And then the other situation is that, of course, we could reject our null hypothesis. But if our null hypothesis was actually true, but we rejected it, we called that a type 1 error. If we failed to reject it when indeed it was actually false, then we had a type 2 error. Right? And if we rejected the null hypothesis and it really was false, then of course there's no error involved. Right? And so we called the probability that was associated with the type 1 error, that's your alpha, and that's also our level of significance in our test. Right? Versus the other error, we called that beta, and that's associated with the probability of a type 2 error. Right, so our test statistic here, just like in our confidence intervals, was associated with whether we knew or we did not know the variance. Right, and this is again for the true mean here. If this was known, we would use the test statistic z, and if not, we were going to use the t statistic with n minus 1 degrees of freedom. Right? Now, in terms of computing our beta, that leads us to the operating characteristic curves. And knowing those, we can actually do a design of the experiment to come up with what the sample size is for the combination of alpha and beta that we find is acceptable. But that's one of the yin and yang aspects of this, is that we have to balance alpha and beta. We can't drive one down incredibly small without driving the other correspondingly up. So there has to be some sort of balance between those two. Right? And remember that 1 minus beta was defined as our power, and that's essentially our probability that we reject H naught when H1 is true. Okay. Right now, in terms of making that final decision, remember there's two different ways that we could make the actual decision. We could compare the observed p-value to alpha, right? So we go and we calculate the test statistic and get the associated p-value that goes along with that probability that we're outside of that, either one-sided or two-sided, and compare it to our alpha value that we've chosen. Or we can compare the test statistic to the threshold value. So that would be, for instance, we could go calculate z naught and compare that to z alpha over 2. So two different approaches that we can do. What you'll oftentimes see people do is do both and report out both, because that's what comes out of your typical software. Right now, on tests for variance, we're looking at the null hypothesis being, okay, this is again single sample here. Right, so under our null hypothesis, our variance equal to some value, and then our test statistic will be chi-squared, and we'll calculate it as n minus 1 times our sample variance divided by this value of interest, and then go make our decision based upon the p-val in the same way, or compare this test statistic to the threshold value that goes along with the alpha value. And in a similar way for the population proportion and dealing with the approximation to the normal, then we can use z naught is equal to x minus n times p naught over square root of n p naught times 1 minus p naught. Of course, you could do this also as your p hat divided by n minus p naught, and then you get, right, so factor out the n here, and that's where you get this guy right here, and so that'd just be 1 over, oops, yeah, no, sorry, had a momentary lapse. Right, so if we factor out the n here, then we get n times all of this, right? And so that becomes n times x over n. X over n is our p hat, right? So we have an n sitting out. Take it down into here if we want, or you can just leave it sitting out there if you want as well. Leaving you with the n factored out like that. And I'm just going to leave the numerator down like so, and you can work with it in all kinds of different ways that you want to work with it. Right now, when it comes to then two samples, when we start doing comparisons, then the differences in those means, for shorthand reasons, let's look at two population means and call that delta, and the observed one being delta naught, or I should say the target. And so now the test statistic that we're looking at in those differences is the observed x bar minus x2 minus our delta 0 all over then the standard deviation. How you write this in the denominator depends a little bit upon your situation that you're looking at, but in a more general case, we've got the variances divided by the respective sample sizes, and that test statistic is going to be z if our variances are known, and if not, then we get a t-distribution with new degrees of freedom if we're estimating using, say, the sample variances. And that new expression is somewhat complicated, and if you need to do it in the general case, then take a look at it. Your textbook, of course, has some simplified approaches, some pooled approaches under certain kinds of special cases. Right? The tests on paired t-tests are really just a special case of single samples, where now we don't treat our x and y data separately. They're paired, and we do the difference directly on each and every one. So if we have n paired data points, then we'll have n values for the difference, and now we can just go and do the regular t-test that we saw up above. Okay. For tests on ratios of variances, the general test statistic was to go to the F distribution, where we were looking at the ratio of the sample variance to its true variance, and on top of, or in the numerator and the denominator, then we get the second one. Now, under your typical null hypothesis, those two variances from the population are the same. So obviously we can cancel that all out, and from a pragmatic standpoint, then our test statistic is just a ratio of the two sample variances. And then finally, for test on differences in proportions, typical null hypothesis that the proportions are the same, and so our test statistic is z. If they're the same, then all we're left in the numerator is the difference. You can write the minus, but they're the same, right? So minus the difference, but they'd be the same. That should be 0. And then you get p hat times 1 minus p hat times 1 over n1 plus 1 over n2, and where p hat is really a pooled version here, x1 plus x2 over n1 plus n2 quantity. Now keep in mind again that the constraints here on all these proportions are that p isn't too small, it's not too large, it's not real close to 0, not real close to 1. That somehow it's more out in the body than it is out in the margins.